Well, good morning and welcome to AIEC Webinar Weeks. We're glad you decided to join us this morning. We hope everyone had a wonderful Thanksgiving holiday. We are having a little bit of technical difficulties this morning with our links. So we're hoping that we get some additional attendees joining as we work through our housekeeping items this morning. Today's topic is going to be Introduction to Distribution Automation. This is the first of 4 webinars today. If you're interested in attending one of our other webinars, please visit aiec.coop/webinar weeks. Those will be available for registration, I believe, up until 1 hour before the webinar. However, if you can't meet that deadline, reach out to Ashley Graham and she'll be sure to take care of that for you and make sure that you can get into that. Our presentation will last approximately 45 minutes today. We'll leave some time for Q&A. I believe our presenter will be breaking intermittently for questions throughout his presentation. Please use the chat function to submit your questions to AIEC directly. You want to select a little drop-down box, select AIEC, and we will moderate those questions for you to our presenter. Again, always keep your microphones muted if possible. And I think that's all I have. Brian, if we have an attendee that's interested in PE credits, what do they need to do?
If you have not already attended any of our webinars and or sent me an email yet, please send me an email if you are a PE and would like those PE credits. I've been keeping track of those that have reached out, and so after next week, I will tally all the sessions that you attended and get you out one big certificate. I'm not going to do it for each individual class. I'll just list the classes on one joint certificate for all of the webinars. So shoot me an email just to make sure I'm keeping track of yours. My email is badams@aiec.coop. So shoot me an email. And then I'll introduce Eric real quick. Eric Brandstetter is a Senior Business Development Manager for G&W Electric and is based out of Washington, D.C. Prior to joining the G&W Power Grid Automation team in 2015, he spent 6 years working for ABB, both in the U.S. and Germany. Eric has 10+ years of industry experience, including relays, remote terminal units, medium voltage switchgear, and communication equipment. So with that, I'll hand it over to you, Eric.
Thank you. Thanks, everybody, and welcome. I'm honored to present to you this morning and have prepared the presentation that you should be able to see on your screen with the following agenda. We'll talk about some of those points here in more detail, and these points are really going to be an acronym that you see on the point 4, FLISR, as well as the point following there, script versus model-based automation. And then the other bullet point that I want to spend more time on is application examples, and really with the idea of the audience taking some ideas, hopefully, away from this of what's possible with distribution automation and as it relates to other co-ops and projects that have been executed. So let's start with what causes non-planned power outages. And this is from an investor-owned utility, as you can see in the reference down there from We Energies. But it's pretty representative, I would say, of a utility or a co-op with quite a few overhead lines. And if you're looking at that pie chart, a good half or even more of a half chunk is done through is caused by equipment or weather. And then you have additionally, fallen trees and animal contact. So summing all of this up, there's quite a few external components really that cause non-planned power outages, and today we're talking more about how to respond to those non-planned power outages in a faster and safer manner. So why automate in the first place? And these 4 bullet points are bullet points that I gathered just from discussions with you know, with peers as well as customers in all sectors, really. And the first point is shorten power restoration times from hours to minutes, seconds, and even cycles. And when we talk about one of those acronyms, FLISR, I'll go a little bit more into details of how we accomplish this. But the idea is really, you know, cutting down on those outage times of after a storm and restoring power, taking hours, maybe sometimes even days, you know, if it is a bad situation, and cutting this down to the ranges of minutes. Second point is significantly improving reliability, really as a result almost as of the first point. And if you're looking at reliability indices that I'm listing there as per IEEE 1366, those are ways of measuring really how reliable your system is, and put some numbers on that. Third point that I'm making here is improve operator safety. What I mean by that is that with automation, you increase operator safety by not putting a lineman in front of a live device, or worse, in front of a faulty device, or in front of a device that might be, you know, in a vault submerged with water after a storm, or where the operator has to maneuver in tight spaces to hook stick operate equipment. With automation, you can eliminate that factor either by automatically switching the devices or moving to, let's say, a push button operation on a relay on an electronic device that then is really on a 120 AC side rather than, you know, 4 kV and up. And the last point on why to automate I have on here is maximize existing infrastructure investments. I personally think that is a very, very important point. And I always look for that when designing any automation system, is really what's already there, to not throw things out that are, you know, that you've invested in the past, and utilizing as much of the existing infrastructure, such as switchgear, SCADA systems, and communication equipment as possible. When we're talking automation, we need to lay the foundation of automation components. So which pieces do we really need to have in place first before we can even start talking automation? First, you need a device that does the actual operation. I think all of you have these on your systems, either switches, reclosers, substation breakers, things of that nature. Second component is control power, and that's needed to power the microprocessor relay that you see there. And then the fourth point is the motor operators or magnetic actuators, and these are essentially replacing the human muscle power that is required to open and close switches in a manual switch. Having a motor operator there together with a relay that sends a command to that motor operator to open and close a switch is required for automation. And then lastly, current and voltage sensors for determining fault currents really, and locating faults, as well as getting an idea of presence and absence of voltages as your sources are concerned, along with automation programming. And I mentioned initially that I want to spend a little bit more time on script versus model-based automation, because that is, it might not be an industry term necessarily, but it's definitely an industry-wide approach to automation, and I wanted to share this with you today. The last point here I have as optional, and I have it as optional because it's truly not a mandatory requirement to do automation. Communication is optional for automation. There are many non-communicating automation schemes out there, but adding communication will add some features. I'll talk about that a little bit later. Any type of computer or server is optional. Any type of human-machine interface, right, like a graphical view of the system is optional, and so is a SCADA system. Some of you might have a SCADA system. Some might use the SCADA system of your G&T. Or you might not even look at it at all. But as automation is concerned, it is definitely not a mandatory requirement. Just threw a couple of pictures on here so we don't look at bullet points only. Select automation components, really. I talked about relays. You see an ABB relay and you see an SEL relay that we work with a lot. You see a recloser up there and you see a pad mount switch. So those are just some examples of those components that I mentioned, along with PTs, in both pictures, really. One solid dielectric, the other one oil PT to provide that control power. All right, here's the first acronym of the day, and I think I want to go through this first here and then open it up for questions and see if you have any questions already. Go through this here and then take a little pause. So one of the fun acronyms in the industry is FLISR, and FLISR stands for fault, location, isolation, and service restoration. And that's, you know, sounds like a lot, but it's essentially everything you already do manually in an automated, faster, and safer way. Meaning, if you do have a fault in the system, you will need to be notified by it one way or another, either customers calling in or having some kind of fault indication on your system. Then you need to locate the fault, right? So we have a fault location. Then you need to send typically a crew out there to isolate the fault so that it can be worked on or repaired. And that's true for overhead lines as well as underground faults. And then, you know, you need to look at your system architecture together with your operators on where and how you can restore power safely to as many customers as possible that are not affected by that fault, right? So that's a typical sequence of operation in FLISR, is essentially that in the automation world. The goal, as I initially mentioned, is to cut down on operation times for power restoration. So bringing this down from hours to a couple of minutes, and I have a graphic illustrating that. The first graphic that we're going to look at here is the impact on customers without FLISR. And we have two substations here, one in the north and one in the south, and you see a tie point between your substations with an open switch. Let's see if I can use my laser pointer here. So an open position here, right in the middle of the system, essentially, with the substation in the north feeding all of these loads and the substation in the south feeding all of these loads down here. So now we have a fault occurring in this little simulation here, and we have this fault occurring here in the south. As a first operation, the substation breaker trips and essentially isolates this entire section down here. Well, then you most likely would get calls from these customers, all of them affected by this fault, anywhere between 1 and 10 minutes. And don't hold me to those times here. It's just to get the point across of the differences with and without FLISR. After discovering the fault and knowing of the fault, a crew is typically deployed, and depending on your where you are in the country and where the substation is in relation to your operations center, that travel time can vary, right? As an example here, I say half hour to 45 minutes. Driving down the line, in this case, overhead lines, locating the fault, might be animal contact, might be a tree, down conductor, something like that. And then go through manual switching for partial restoration. And the partial restoration here means that we are opening upstream and downstream of the fault to isolate the fault. We're closing in the tie if we have the luxury of having a tie, and if the substation in the north has the capacity to pick up those loads down here in the south. And then as a last step, close the substation breaker back in. So now we're having the fault isolated here, and we have a partial restoration, as I call it, in a matter of an hour to an hour and a half, right? So this is a probably good optimistic estimate. If this happens during a major snowstorm, if that happens along with additional operations in the area or in the middle of the night, those numbers might go up. So let's now look at the last thing here I should mention is the repair time. Again, that is the same across the board. It takes anywhere between an hour or 4 hours. It might even take longer depending on what what the fault did to the system, and then returning to a normal state, meaning, you know, we're opening our tie again here, and we're closing those two isolating devices here, and the crew goes back. So now let's look at the same example here for customers with FLISR, right? Same system setup, same fault occurs, and now we are doing a switching operation that is essentially doing the partial restoration in less than 5 minutes. So before that, we had to deploy a crew, isolate the fault, and do the manual switching operation of closing the tie point and closing the substation breaker back in to supply power to this one section here that is not affected by the fault. And it took, you know, a good amount of time to do so, because it was a manual operation and you actually needed to deploy a crew. Now with automatic operation, the goal, and that's defined in IEEE standards, is to keep that less than 5 minutes, to do that partial restoration in less than 5 minutes. Still, you know, for a crew then to be notified and say, hey, you know, automation system operated, or customers still calling in and saying, hey, we are affected by a fault, that's around the same time. The repair time also doesn't change. But what's important is that, you know, this first initial partial restoration, meaning that you supply customers not affected by the fault with power as quickly as possible, happens in a matter of minutes and no longer in a matter of hours. I have 2 slides really on the monetary benefits on here, and the first one is really looking at the indices as far as duration and frequency of outages goes. The U.S. Department of Energy issues these reports, I want to say every 5 years. So this one is a little bit older, from 2014, but it looked at 266 of these FLISR operations that we just went through, and you can see the improvements here. Those are average improvements. So durations of outages went down by 51%. The frequency of outages went down by 45%. And the customer interrupted minutes go down as a result. So there is proof over time and across different utilities that FLISR does improve your reliability. And what does that do from a monetary perspective? And here it's just one example, right? So for 5 large industrial customers on that loop, and that might not be applicable to you. Maybe you have one industrial customer, but maybe you have just one critical load, right? That critical load can be maybe a gas station out there. It can maybe be, you know, a hospital. We have projects where the critical load is the single family home of the mayor of the town, just because, you know, you don't want to upset him or her, and we want to supply good power to that single family home. That could be a critical load. But as far as money is concerned, this graph here essentially shows that, and that's pretty typical, I would say, that a return of investment happens for an automation system of that size within like 1.5 years or 2, if you just have one event or 2 events a year. And I'll talk about this a little bit later as it relates to your potential automation projects and where to start. And before moving into the communication aspect of things, I wanted to make a point on single-phase FLISR. So everything we just looked at the example there with the graph was really 3-phase FLISR, meaning if you have a fault on a phase, for example, probably most likely, as the statistics show here, it's going to be a line to ground fault up to 65 to 70%. You essentially trip out all 3 phases, right? And if you have residential loads on those 3 phases, the residential loads that are being fed by phase B and phase C are being affected by that A phase fault. With single phase FLISR, you basically eliminate that. and isolate only those phases affected by the fault. And then in turn, again, it makes a huge improvement on your reliability numbers if you implement single phase FLISR. The last point I'm making here is that model-based single-phase FLISR is much easier to implement and maintain as script-based, and we haven't talked about model versus script yet, but we'll get there, and I'll show you why and how. Okay, let me close my blinds here real quick to not have the sun in my eyes, and I'll open it up for questions to see if there are any at this time. All right, I'll take that as a no for now. If there are any at this time, let me know. You can address them, and I'll take another couple of pauses throughout my presentation. Script versus model-based automation. So as I said before, I don't think it's necessarily, an industry-wide term, but let me explain, at least from my perspective, the different approaches to automation, and those approaches are definitely industry-wide applicable. Just a question of how you coin it as far as terminology goes. I like script versus model, and I tell you why. Script-based automation. Script-based automation is literally writing a script or hard-coding logic inside a device. So some engineer or programmer is looking at your system architecture, looking at your one-line diagram that you want to automate, and basically looks at the sources that are available, looks at the switching devices that are available, and looks at the line sections that connect sources and switching devices, as well as your loads. And then really looking at the system and say, okay, what happens if a fault occurs in section A, in section B, in section C, and so on. And as a result, then writes a logic, almost like an if-then-else logic. I'm making the point here on the left, saying, if a fault happens here, open this device, close this device, and so on. What you get from that is a static system response to those contingencies and those steps that have been programmed ahead of time. In other words, if a storm comes through and it creates a fault or a situation on that portion of your grid where you have that automation system running that was not thought of before during the design phase, and as a result wasn't programmed into the devices, it's not going to operate on it, right? So the system is only as smart as we are, so to speak, based on predefined contingencies. The third point here on the right is that as a result, with this type of automation, you can only turn it on or off. And I'm making this point here because it's important for operators who are transitioning from a purely manual operation to an automatic operation, right? So before, all hot stick operation and manually opening and closing switches, and all of a sudden you're basically saying, well, it has an automation system now and it's gonna do its magic all by itself. That can be a pretty big leap to go there. And we'll look at what model-based automation offers as an alternative. And then limited support of advanced applications. I'll talk about this a little bit later. But let's look at model-based automation first. So as opposed to script-based automation, the model-based automation is looking at that same one-line diagram, at that same section, but now models it in a software, right? So I'm making the analogy here to Google Maps. Think about it in your part of the country. Google Maps has all the streets and roads mapped out, and it essentially takes real-time information from everybody out there, including traffic, all the cars on the roads, including any roadblocks, including even toll roads and anything else information-wise that it can get, and brings that back into an automation system, if you will, that when you say, I want to go from home to work, and I want to see what the fastest and best route is, it might change that route dynamically. So now you have a dynamic system rather than a static system, and it's dynamically responding to faults. In other words, it uses real-time information to make its decision rather than the scripted logic of like an if then else. And that really allows for a lot of flexibility, especially when it comes to changing the system in the future. Adding a device, for example, is much easier to accommodate because you don't need to rewrite any scripts. You basically do a drag and drop automation engineering approach and add those devices. And it also has a couple of additional features that I want to talk about next here. Before I go there, though, is that I want to make the point about this operation modes that we talked about for the script-based logic. So here you have now a semi-automatic mode. When it comes to that transition, especially for operators to go to automation, that semi-automatic mode, what it does is it isolates the fault, but before restoring, it creates an operators table for you to look at. And it says, okay, I analyze the system in such a way, and here are the switching operations that I suggest as a software, essentially. And you can go through them by one and operate them step by step, or you can operate them as a sequence, or you can switch things around based on your system and your experience. So the system over time gets better and learns how your system is configured and what your standard operation procedures are, rather than accounting for them, trying to account for them on the front end. So the comparison here between script and model-based in this table is mentioning all these points that I brought up before. What I didn't mention before is like a rule of thumb, and again, that is something from our own experience, that as soon as you exceed 10 devices that you want to have participate in your automation system, a script-based solution is no longer the best way to go from an engineering effort as well as from an economical point of view. And I'm saying this because a system or a one-line diagram with 10 devices can get pretty complex, right? You might have a loop here, you might have a radial feed here, and then you have to think, for a script-based system, you have to think of all these contingencies, and more importantly, you have to test all of this before it's being deployed. And that gets, it gets just too complex and too hard to manage and to test. Therefore, the recommendation there is to go with model-based automation at that point. And that's true for the scalability of the system as well. I think I mentioned it before, where when you add devices to a script-based solution, you need to typically touch the logic again and say, hey, now you don't have just 5 devices participating on automation, now you have a 6th device, and therefore you get an additional contingency. That's much easier to do with a model-based automation. So how do I sum this all up? And I found this picture online. I give the source here in the bottom, but I found it pretty fitting, as in, like, you know, a programmer person that does the script versus more like a robot type who does machine learning and responding to faults on the system dynamically rather than through a static response that was previously scripted. So the question then becomes when to go from script to model. And this is when you already know that you're going to have future expansions on that same system. We'll talk about this towards the end of the presentation as to where to start, at least what my recommendation is, where to start with automation and where to go from there. But if you already know, that you're planning to automate more parts of your system, then it might be a good idea to take a look at model-based automation. The second point I already made, too many user-definable contingencies that could be fault locations, reconfiguration scenarios, change in protection settings groups, directional power flow, things like that. And then the threshold there between 10 to 15, I say here, but it's really right around 10 when it gets quite complex. And then when advanced applications are required. And what are advanced applications? And in that context, I list all of them here, but I want to point a few out. Integration of renewable energy resources or distributed energy resources is one, and we're seeing a trend in the industry where more and more of those pretty sizable microgrid projects actually are popping up with co-ops. Then the integration of and connection with existing SCADA systems is one point. So if you already have your own SCADA system, or if your G&T has a SCADA system and you would like to integrate and connect that, that is much easier to do with a model-based automation solution to share data at that point. Email and text event notification, including remote and mobile device viewing access and alarms is a point. Again, in this day and age, we have our mobile devices with us all the time, and most field crew now has iPads or laptops on their trucks, and therefore model-based solutions give the opportunity to see the system on those devices. And then, you know, integration of other sources such as weather metering information and things like that into an automation system can be easily accomplished with a model-based automation solution. I'm having two pictures here for an example of those advanced applications. One is what we call an IAD control panel, and that's really nothing else but a picture of an actual device that is sitting in the field. I'm having two examples here. One is a recloser control. The other one is a meter. And over that picture, we basically lay those data points that we're getting from that field device in that software. And what that does is it really shows the same faceplate as your field crew would see standing in front of the device, right? So the person that is standing physically in front of the device in the field has the same look and feel as the person that is sitting, you know, at the computer or at the head end on the operations center. And that makes communication much easier, especially if you're thinking automation and doing this for the first time. It closes a gap there. And the second point is mobile applications to view system status and alarms on phones and tablets. That is a nice feature that basically tells you what's going on in your system with as many data points as you want, really, and map views and outage locations as determined by the automation system. I'm underlining view because as soon as we get into software and automation, really, we are talking about cybersecurity as well. So this feature is only able to look at stuff, and you will never be able to operate things remotely, at least not from this secure mobile interface. All right, lots of talk on my side again. I'm breaking here to see if we have any questions. As a next step, we will go into communication infrastructure, since this is important. No questions at this time, thank you. We'll talk about communication infrastructures, and then we'll spend a good 20 minutes on application examples. Communication, I keep short and sweet. It's really the question of yes or no. If the answer is no, we don't have a communication infrastructure in place, but we want to do automation, then the answer is let's do non-communicating automation schemes. I call it the grandfather of automation because it has been around the longest, really. And it's timer-based and voltage and current-based, essentially. So you're using the devices that you have in the field, and you program some logic in there to make switching decisions purely based off voltages and currents, including some timers. If you do have communication in place, or you plan to deploy it, then it opens a bunch more options for real-time information. One point I forgot to make is that for model-based automation that we talked about, since it is a software-based solution, it does require communication. So that is a mandatory requirement. That's the point that I'm making down there. But even if you need like a centralized view of your system in a way, you would need communication. Or if you're looking at a peer-to-peer automation scheme, you would need communication between those between those devices in the field. But all of that, again, will need to be discussed as part of any automation project. Really, communication is just one talking point. All right, let's go into the application examples. And I really want to spend here probably 10 to 15 minutes on this to go through some examples that hopefully provide some insight to you. First one is an automatic source transfer. When I was talking about critical loads before, that is one of these examples. It is very straightforward, and it's a fast deployment as well as a fast return on investment when it comes to automation. In this scenario here with the co-op in Missouri, it is protecting a truck stop. We're talking about two reclosers. In this case, they're communicating wirelessly through 900 megahertz radios, and they're restoring power to this critical load. It's a Flying J travel center or truck stop within 6 seconds. So while before the truck stop experienced outages in the ranges of hours, now if there is an issue on those overhead lines supplying power, there's an alternate source that can switch in within 6 seconds. Question then becomes, okay, great, it has a communicating scheme where the two reclosers talk to each other, but what if that is compromised? Then there is a backup non-communicating scheme that still provides backup power in a matter of minutes. We're looking at 2 minutes, including the timers that I mentioned before. This is what a simplified one-line including communication diagram looked like for this application. So you have the critical load in the middle. You have a normally closed source one recloser, meaning in a normal state, the source one is supplying power to that load. And you have a normally open recloser for source two. If you do have a fault, the normally closed a fault or really a loss of source in either way, the normally closed recloser opens and the normally open recloser closes to supply power. We're looking at the radio communication here, and then the one thing I didn't mention yet is that this customer also has communication back to SCADA using an additional radio at a local substation tower. Second application is loss of voltage, which is what LOV stands for, and auto restore closing. So this time, again, critical load, larger in design. That's really in my neck of the woods here. I'm based out of Northern Virginia, and the data center deployments in what they call Data Center Alley in Loudoun County is really going through the roof right now. For several reasons. Tax incentives is one, and the strong fiber backhaul infrastructure is another. But data centers are really conscious about reliability and redundancy when it comes to power supply. So in this case, it's an application with a underground switch, right? So a pad mount switch. We are having a bunch of relays, metering PTs and external metering CTs with accuracies of 0.5% because the data center wants to know what all of their customers are actually using to build them. So this is a co-location data center, meaning that they supply server space to third parties and charge them based on really square footage and usage. What we provided here is programming for arc flash reduction mode and an automatic open upon loss of voltage with a staggered closing upon returning of the source. So if Dominion is the utility here, if the feed from Dominion is lost, we will see an automatic open, and then you have a bunch of UPSs and backups and generators that are taking over. But as soon as the utility voltage comes back, each and every single way on the switch with the associated loads is being closed and staggered to avoid a high inrush current and to bring the big loads basically on in a staggered manner. Just a few pictures of what that looks like. So just to show you basically some scalability of automation. Before we talked about overhead and 2 reclosers. Now we're talking about underground with SF6 gas switchgear and a larger footprint really. Third application example here is a centralized remote monitoring and control. So with this co-op, the goal was really to have their own SCADA system. They have a GMT and they use the SCADA system, but really just for status and control of the substation breakers. This co-op, to improve reliability, invested in reclosers. They started with 3 new reclosers, but they said, now that we have these reclosers, we would really like the way to monitor them remotely and also be able to operate them remotely rather than going out to each and every single recloser and push button operate them. So what was provided here is, and you see here it's Cimarron Electric, was a system that shows the overall network of Cimarron Electric on the top left. And then you can drill down to each and every single individual recloser where you get all the measurements and that faceplate that I mentioned and showed initially, from where you can operate or from where you can look at what you can look at really together with your operators in the field. So another way of doing automation, in this case, no automatic switching, but enabling remote monitoring and control of your field devices. Going a step up, and I structured these application examples in a way that we are showing essentially a stagger or a graded approach as it comes to scalability, starting with something rather small and then scaling it up. So we're going further up here with a centralized model-based single-phase FLISR and loss of voltage for co-op in Ohio. And here the challenge was really around residential loads and the reliability with single phase loads. They really wanted to improve the reliability numbers in that area, and they went with a centralized model-based solution. And at the time, in the industry really, there was no model-based single-phase FLISR solution, and that is something that we developed together with this customer. A couple of screens here. You can see it looks more like a SCADA system in this way, with simplified one-line diagrams, with alarms, with status pages, and things like that. All of these devices, 14 reclosers total, are working in a fully automated system to this day. One other slide here, again, showing those control interfaces. Have this slide in here because I wanted to show you that pretty much any control interface can be modeled in this system, not just Schweitzer or meters as I showed before, but also in this case, Cooper Form 6 controls. And this is the final application example that I want to make, and it's a nice one because it's been around for a while. Central Georgia EMC, you can look it up. Aaron Herschel is our point of contact there, and he's given several presentations at various trade shows back in the day, almost, I have to say, when we were still allowed to attend trade shows in person. But Central Georgia invested heavily in reliability improvements with a goal up there to reduce their duration of outages from 130 minutes to 84. And with a result of bringing that down really to 69 minutes within about 2 years. So what this shows is, and there's plenty of papers really available that you can find online just by looking at Central Georgia EMC FLISR. That shows that, you know, the return on investment there happened really, really quickly, even though it was a very, very large investment. And the reduction of about 5 million in total outage costs so far, and that was really a couple years ago already. So I think the initial reduction there is huge, and then over time, you know, it fans out a little bit. But if you take into account what your cost of an outage is, and that could be, you know, the loss of a critical load, crews to be deployed, and things like that, that is different for every single utility. But for them, it was a huge improvement, not just in the reliability aspect, but also in the cost of total outages. Okay, I'm breaking here again for questions. There might be questions associated with any of these application examples that I've given at this time. I'm nearing the end of my presentation. I want to talk about testing, and then I want to talk about the last point of where to start with automation before I'm finishing up. Okay, no questions yet. Factory acceptance testing. So the importance of testing is crucial to automation, at least from my experience. So not only do you take, you know, a leap really from manual operation to automatic operation, but you also need to instill trust that this automation system actually works the way that we designed it. And designing it together with all key parties, including, you know, operators and engineers, is one thing, but really putting it through its paces and testing it with the actual live equipment and with the actual communication infrastructure, if there is one, and, you know, pushing all the buttons and kicking the tires, so to speak, is very, very important. And at least for all of my projects, has been proven very, very valuable to go through that effort and do that in a climate controlled and safe environment, and invite really operators to this to receive a first round of training and to get more familiar with the system and ask questions and such. So the idea here is to test the automation system, and then after it has been tested and verified in a factory environment that it works the way it should, then deploy it, and as a result, really cut down on those commissioning times on site. All right, I'm finishing up here with where to start. And that's just, again, my perspective or recommendation here based off today's webinar and future discussions. Attend user events, just like the one today, to see what's available out there and what others are doing. That's what I wanted to do today, show you what's out there and what other co-ops have been implementing. Then if you really identify a potential portion of your grid that could benefit from some automation, identify those circuits and start with critical loads or with circuits that experience frequent outages. Maybe, you know, lots of vegetation around it, maybe a longer line with lots of wind or something like that, and critical loads we already talked about. Next step from there would be to have a single line ready and that show these circuits, and then schedule meetings with vendors to determine the best fitting solution, right? So have different vendors take a look at that and see what they would propose. Okay, so closing this webinar out today with these key takeaways. 3 of them that I would like you to take with you is, first, there are many ways to automate. Start small and grow is my recommendation. Automation can be overwhelming at times, but I'm trying to get across that it doesn't have to be. So starting typically with a small project, let's say those 2 recloses for a critical load that we had as one of the application examples, might be good and makes it more digestible. And then add on to the systems that you already do have. So whatever is already in place, you know, utilize that. Look around to see what vendors can provide to automate your system based on how you want to automate. And there are a few vendors out there that do that. And talk to your colleagues and other utilities, co-ops, munis, C&I customers to see what they are doing to automate. And that's, I think that's a little bit challenging given the times now, since most of my conversations, at least of that nature, typically happen at industry events and trade shows and such. And in the virtual world, it's a little bit harder to do. but still, I think it's a good way of really giving you an idea of what might make sense for your system. That being said, I'm closing out my presentation, and I have a few questions prepared since we didn't get any questions. I'm not quite sure how many attendees we have on here, and I didn't really create a poll or so in Zoom where we could see the answers, but looking at the time here as well, we may or may not get to these questions. In any case, I wanted to say thank you for your attention, and hope to have provided some input for you today. Thank you.
Well, thank you for that, Eric. We definitely appreciate your time today. The chat is still available if anyone has any questions. We still have a few minutes here. Eric, also, if you wanted to ask some questions to the attendees, that would be perfectly fine at this time as well. While you're thinking about that, I just want a quick plug here. Our next webinar will be up at 10:30, and that will be backup best practices. So if you haven't registered for that, please reach out to Ashley Graham. She'll make sure to get you taken care of for that. And at this time, Eric, we still don't have any questions for you. You must have done a phenomenal job presenting the material, so that's a good thing.
Either that or everybody's asleep already. So,
hey, real quick, if there's any further questions or someone wants to follow up with you, there's good. There's your contact information. We want to make sure that everyone has that information. Yeah,
please reach out to me either by phone or by email. I'm not sure, but what your thoughts are, but I'm happy to share that presentation if that is something that AEIC is doing as a result of these webinar series.
Yeah, so with your permission, we're making these webinars available online via YouTube. So Ashley will be putting together some information that she'll be sending out to folks so that they know how to access these webinar series.
Okay, excellent. Yep.
All right, well, if there's nothing left here, we'll give a little bit of time back. And again, Eric, thank you so much for your time today, and we wish you all the best.
You're welcome. Same to you, and thanks for the opportunity again.
Bye now.
Bye now.